Hi, my name is Tucker, and today I will be explaining my research project to you guys. So, my research project was on the effects that UV radiation has on the normal human microbiota of the skin while being protected by sunscreen. So, before getting into the results of this research project, first I want to introduce you guys and let you know all the materials that were being used and everything like that. So first, we were given two different types of human skin microbiota. The first one being Propionibacterium acnes, and the second was Bacillus subtilis. During this experiment, different sunscreens were tested under 6 inches of UV radiation at different times to see how well and how long the sunscreen protected the microbiota. The sunscreens that were used during the experiment was Coppertone SPF 15, Coppertone SPF 30, and Coppertone SPF 50. Each one of these sunscreens have different levels of protections, so we can see just about how long each one will last underneath the 6 inches of UV light. So this slide right here is just another introduction slide, give you guys more of a background on the different types of flora on the human skin. So there are many different types of flora on the human skin, such as Staphylococcus epidermis, Staphylococcus aureus, Corynebacterium, the bacteria we're using, Propionibacterium acnes, and Micrococcus luteus. All of these are very common types of flora on the human skin. So this slide here is just another introduction slide. It's continued on, and this is also giving more background to what the normal flora on our skin does for us in our everyday lives. And these things include actions such as protection against pathogens, immune system support, it maintains a very healthy skin barrier, and it also helps our wounds heal faster. And then over here to the right, I put all of the references where I got this information just in case you'd like to fact check me or anything like that. So now that we've went over how the normal flora on our skin helps us, let's go over what would happen if we didn't have this microbiota on the skin. If we didn't have normal skin flora, our skin would be highly vulnerable to infections, inflammation, and dysregulated immune responses. These microbes are not just harmless passengers, they actively protect us and maintain skin health. And then again, I put references over here to the right where I got all this information. If you would like to fact check me, I can put all the links in the end. So now that we're out of the introductory phase, we can actually get into the interesting part of this experiment. So my goal with this experiment is to investigate the effectiveness that different sunscreens have against UV radiation for different amounts of time. This study also aims to understand how UV effects can differentiate between different levels of sunscreen. This, in the end, will promote skin health and raise awareness to the effects that UV radiation has on our skin as a whole. So some of the materials used was the two bacteria we had was Propionibacterium acnes and Bacillus subtilis. The different sunscreens that we used was Coppertone SPF 15, Coppertone SPF 30, and Coppertone SPF 50. Now the materials used while completing this experiment included a wire loop, a Bunsen flame, a nutrients agar plate, blood agar plate, a big jar, and a candle. So the active ingredients in each sunscreen varies just a little bit. They're all about the same ingredients, just different levels of the same ingredients. So in Coppertone SPF 15, avobenzone is about 2%, homosalate is about 5%, octisalate is about 4.5%, and octreosilane is about 3%. And then after that, we get into Coppertone SPF 30, where you see these levels rise just a tad bit. So avobenzone is at 3% now, homosalate is at 8%, octisalate is now at, or still at 4.5%, and then octocrylene is at 6% now. And then we upped these percentages even more in Coppertone SPF 50. Avobenzone is still at 3%, just like it was at SPF 30, but now homosalate has been increased to 10%. Octisalate is still at 4.5%, and then octocrylene was also increased at SPF 50 up to 8% from 6%, which we saw at the previous SPF 30. And this down here is a picture of the materials we used. You can see the jar, the candle, all the bacteria in there. You can't quite see the wire loop there, but it is there, I promise. So now we can actually get into the first day of experiments. On our first day of experiments, after receiving the bacterium that was selected for us, we created 4 different dilutions of broth and bacteria. The first thing we did was take 1 microliter of Propionibacterium acnes and put it into a broth that we later then spread on our blood agar plates. So we took that 1 microliter of Propionibacterium acnes and put it into 9 microliters of the special broth, which then created a 1 in 10 dilution. After that, we took another 1 microliter of the 1 in 10 dilution and put it into another 9 microliters of the broth, creating a 1 in 100 dilution. After making our 1 in 100 dilutions, we took another 1 microliter of that broth and dilution and put it into another 9 microliters of another tube of broth and create a 1 in 1000 dilution. We did this one more time and ended up with a 1 in 10,000 dilution, which is what we actually spread onto our blood agar plates. So now I believe we get to our second day of experimenting. So on March 27th, me and my partner started off our experiment by using the aseptic technique to streak our blood agar plates with the bacteria P. acnes, and we placed 100 microliters of P. acnes on our blood agar plates. After streaking these plates, we let them air dry and then placed them in a massive jar, lit a candle, and placed it inside the jar with the lid closed. Now, if you know anything about P. acnes, they are anaerobic bacteria, so they cannot have oxygen to grow. So when we lit this candle inside of our jar, it created an anaerobic environment for our P. acnes to grow in. And then after putting all of our plates into the jar and creating that anaerobic environment, we placed this whole jar inside the incubator at 37 degrees Celsius and let it sit over the weekend. After the weekend ended on March 31st, we came back to continue our experiments. Starting off, we created the dilutions needed for Bacillus subtilis, which was 1 microliter of Bacillus subtilis into 9 microliters of a nutrients broth, which in turn created a 1 in 10 dilution of Bacillus subtilis. We did this procedure again, as stated earlier, until we reached the point of having a 1 in 10,000 dilution of Bacillus subtilis. After reaching the dilution necessary, we spread 100 microliters of this mixture onto each of our nutrient agar plates. After we spread 100 microliters of the 1 in 10,000 dilution of Bacillus subtilis, we incubated these plates on their own without a jar or anything at 37 degrees Celsius for another 48 hours. Sadly, when we came back on Thursday, after creating the appropriate agar plate and incubating at 37 degrees Celsius, we realized we had made a huge detrimental mistake. We had incubated inverted, which just means upside down, and sadly that was the opposite of what we were supposed to do. So after pulling these plates out of the incubator, we had realized they had gained way too much condensation for the results to be even close to applicable. Nonetheless, even though those results were not applicable, I still wanted to include the bacillus into our experiment. So instead of covering what did happen, I want to give you guys an idea of what would have happened. So what would have happened was once we put bacillus with SPF 15 under the 6-inch light for 5 seconds, it would have shown us moderate to heavy growth due to exposure time. This exposure time just wasn't long enough to make a significant change. Then it changes a little bit for 10 seconds. So at 10 seconds, it would have shown us little growth, just still due to the short exposure time, but it was just long enough to start killing off some of the bacteria. Now, bacillus with SPF 15 under the 6-inch light for 15 seconds would have shown us minimal growth, maybe not much at all. This is about the point where you'll actually be able to see a difference physically. And then you get into bacillus with SPF 15 under the 6-inch light for 20 seconds would have shown us a major reduction in colonies. It gave us patchy growth, and at this point the SPF would no longer be providing protection. Then we still have 2 more stages at this point, so remember that. Now bacillus with SPF 15 under the 6-inch light for 30 seconds would have shown us serious bacterial death. There would be little to no colonies left at this point. And then for the last one, bacillus with SPF 15 under the 6-inch light for 60 seconds would have shown almost no growth. At this point, SPF is completely gone and bacteria has almost all been killed off. So this experiment with SPF demonstrated that it provides very limited protection for Bacillus subtilis against UV radiation, while short exposure times allowed moderate bacterial growth. Longer UV exposure significantly reduced survival. This shows that low SPF sunscreen offers only temporary protection, and prolonged UV exposure can still cause substantial microbial damage. After going over the results we would have expected to get with Bacillus subtilis with SPF 15 on it, we will now go over the results we would have expected to get with Bacillus with SPF 30 on it. So under the 6-inch light for 5 seconds, we would have still seen heavy growth just due to very short exposure time. 5 seconds just isn't long enough to make a significant change in bacterial growth at all. So, and then we kind of see the same trend for 10 seconds just because we only increased it 5 seconds. So you got to think that's not very long at all. So it still showed us moderate to heavy growth. And then with Bacillus with SPF 30 for under the 6-inch light for 15 seconds, we would have seen a tad bit of declining growth, but still very visible. And then so we're going to move on up to 20 seconds, and this is at the point where we would have seen no SPF left, but growth, the bacteria is still all there. So then we increased it to 30 seconds, and then this is where we would have seen a noticeable drop in bacterial growth, but we would still have some colonies, not very many though. And then under the Bacillus with SPF 30 under the 6-inch light for 60 seconds would have shown us some very, very minimal colonies surviving with very minimal growth. The SPF is completely gone at this point, and it is just knocking bacteria off by the number. After going over the results we would have expected with SPF 30, then we bumped it on up to SPF 50. So Bacillus with SPF 50 under the 6-inch light for 5 seconds would have shown us heavy growth due to just about the same thing for 5 seconds each time. It's just not long enough to make a significant change in bacterial growth. It's just not. And then we kind of see the same trend with 10 seconds. It still is going to show us heavy growth and good colonies. The SPF is still going to be there protecting, holding up strong. And then Bacillus SPF with the SPF 50 under the 6-inch light for 15 seconds would have seen a tad bit of a decrease in bacterial growth, but we're still getting moderate growth and maybe some damage to vegetative cells, but very, very minimal. And then Bacillus with SPF 50 under the 6-inch light for 20 seconds would have shown mild DNA damage, maybe moderate DNA damage to the bacteria, but the SPF would still be protective. And then we bumped it on up for 30 seconds. So Bacillus with SPF 50 under the 6-inch light for 30 seconds would have shown us more damage, and at this point, almost all vegetative cells would have been killed off. But now, for 60 seconds, it shows us actually a pretty good result. So Bacillus with SPF 50 under the 6-inch light for 60 seconds would have shown us very, very minimal growth with only the endospores left from Bacillus. Now you got to remember, these endospores are very, very tough to kill. So that is why there would be only endospores left. So the conclusion that I came to after reading all these possible results of this research project, I came to the conclusion that higher SPF levels just provide much better protection against UVB radiation. And then, so we saw Bacillus without SPF, it showed very, very reduced growth as exposure time increased. While SPF 50 offered the most protection, maintaining growth even after 60 seconds, spores remained largely unaffected in all conditions. But overall, SPF strength directly influences how well Bacillus survived in the UV lights. Now, after going over the whole Bacillus experiment and what it would have been, we can finally get into the things that we completed. So P. acne with SPF 15, we put it under the 6 inches of UV radiation for 5 seconds, and once again it showed us very minimal damage just due to the low exposure time. And then so we bumped it on up for 10 seconds. We saw some reduced growth, but still minimal to medium damage, not very much at all. And then so once we bumped it on up to 15, now this is where we started to see our reduction in bacterial growth. So SPF is starting to kind of fade away, and it's not really protecting the microbiota anymore. And then once you get to 20 seconds, this is where you really see significant damage to microbiota, letting us know that SPF has just been, its threshold has been overwhelmed by UV light. And then, so we bumped it on up to 30 seconds, even after the 20 seconds had almost killed off a lot of our bacteria. We bumped it on up to 30 seconds. And then this is where we saw major damage. So we saw very patchy growth and very minimal colonies. And then once you get on up to 60 seconds of UV exposure, this showed little to no growth at all. And then, so you have to remember, the reason that Bacillus lasted so well was because it has these endospores, and these endospores are so tough. But P. acne does not have these endospores, so almost all microbiota have been killed off at this point. So after going over the results we had with P. acne covered with SPF 15, we'll now go over SPF 30. So under 6 inches of light for 5 seconds, once again, this follows the trend of almost none to minimal damage. Just exposure time is so low. And then you see the same thing in just about the same thing in 10 seconds. It shows a little bit of a change, but nothing significant at all. And then, so we got into 15 seconds. Now this is where we saw a noticeable change in reduction in the growth of the bacterial, but the SPF is still protecting the bacteria at this point, and the DNA of the microbiota is just now starting to be affected. So then we bumped it on up to 20 seconds of 6 inches of UV exposure, and then this showed us a bit more of significant cell damage with moderate growth, and at this point these cells are starting to lose their viability, and if they're exposed for any longer they're just going to be no good. With that saying, we bumped it on up to 30 seconds, and this is where you see a very significant reduction in growth, and then at this point many to almost all of these cells are no longer viable. So at this point, SPF is no longer protecting flora at all. And then we bumped it up again to 60 seconds of UV exposure. This showed us very limited growth to actual no growth at all. Several cells have been killed off at this point, and then you'll also see severe DNA damage in this exposure time. So we saw complete death at the point with 60 seconds of SPF 30. So once we bump the SPF on up to 50, for 5 seconds, once again, no change. Normal growth, SPF is still protecting at full strength. And then, so we bumped it on up to 10 seconds. Very minimal UV stress. So this is actually one of the only experimental phases that we saw a difference between 5 seconds and 10 seconds. Then we bumped it on up to 15 seconds of UV exposure, and this showed us a slight reduced amount in growth, but still more on the normal side of growth. This bacteria is still growing very well under 15 seconds. So with that being said, we bumped it on up to 20 seconds, and this is where we start to see a little bit of reduction in growth. So we saw moderate growth, and then at this point the viability of these cells were also starting to be affected. So then we exposed another agar plate to UV radiation for 30 seconds. Now this showed us significant damage in cell DNA, but still had moderate growth on the blood agar plate. So it is still growing very well. With that being said, we bumped this time on up to 60 seconds of UV radiation, and this showed us significant damage to growth, but SPF at this point is still protecting the flora, but this is at the point where if it is exposed any longer, it will have met its threshold 1,000%. So after completing all of the experiments for Propionibacterium acne with SPF, we came to the conclusion that as SPF levels increased, P. acne showed better survival rate under UVB radiation. SPF 15 offered minimal short-term protection, while SPF 30 delayed damage more effectively, and then SPF 50 provided the highest protection. This actually preserved growth even at longer exposure. However, prolonged UVB radiation exposure still led to reduced growth in all cases, showing that higher SPF slows but doesn't fully prevent UV radiation damage in its non-spore forming bacteria. So at the end of this experiment, we came to the conclusion that SPF does provide minimal protection, but not very much at all. Would not recommend for long exposures of UV radiation. SPF 30 also gives us some protection, but still would not recommend for a long time of exposure to UV radiation. And then SPF 50 is just about the only level of sunscreen that had living cells after 60 seconds under the UV light. So if you applied generously and consistently, SPF 50 would be much more effective than 30, 15, or no sunscreen at all, really. So, with this being said, if you want to maintain skin health, keep your skin protected, consistently apply SPF, at least SPF 50, while being exposed to UV radiation.